Okay, so far we have seen probabilities, entropy, information, Huffman coding. Now it's time for the conditional entropy. If we know how uncertain two events are, two outcomes, with the joint entropy, if then one outcome is given, how does it change the uncertainty? And that is what conditional entropy tells us. Let's look at an example. Suppose we have two friends playing a game. We have Bob, and we have Peter. And this table says the probabilities that either one wins, and here on the left we have Bob and Peter again, but this says who can start the match. We could say it is chess or checkers or any game. Let's make a nice probability table. For Bob, if Bob starts, Bob has a 0.35% of winning, and Peter has a 0.15% of winning. If Peter starts, Bob has a 0.25% of winning, and Peter has a probability of winning. Both are equally likely to start a match. To make it fair, however, it is clear that Bob wins more matches than Peter does. And everything adds up to 1, as is always needed with probability. Now, if we look at these entropy values, we can calculate the entropy of X, and we say that winning is called X and starting is called Y. If we calculate the entropy of X, of winning, then we look at not any value in the table, not these values, but we look at these values, because this just says something about the distribution in winning and nothing about starting or anything. We are just looking at the variable, the outcome X. So that again would be the minus of 0.6 times the 2 log of 0.6 plus 0.4 times the 2 log of 0.4. And this is, in the end, a value of 0.9709. And we can do the same thing, the entropy for who is starting. Well, how uncertain are we who starts? Well, because it is uniform, the probabilities are the same. We can also say this is times 2, or we can also say, well, we just added another time. It is the same thing. And this is an entropy of 1, because both probabilities are the same. As you can see, this we are less uncertain when the probabilities are not exactly the same, and maximally uncertain when they are the same. This is all good. Now, let's say we know what the entropy of we know the entropy of X, we know the entropy of Y. Now let's calculate the joint entropy of both X and Y. Which is the minus, and now we look at the values inside the table. Because these values are dependent on each other, we cannot just multiply 0.6 and 0.5. We have to look at the values in the table. So, we get 0.35 times the 2 log of 0.35 plus 0.15 times the 2 log of 0.15, etc. for 0.25 and the other 0.25. This gives us a value of 1.9406. And as you can see, when we add these two values up, that this is higher than our joint entropy, meaning that these values are indeed dependent. So because this is smaller than the marginals added together, this means they are dependent. So now let's say if we know y, if we know the outcome of who starts, then how does our uncertainty change? And there is one rule that in general, well, let's first look at the conditional entropy formula. This is almost the same as the formula how you would expect it to be. We look at the probability of x is xi given y is yj times 2 log of the same probability that is also here. This probability is also here, multiplied with the probability of y is yj, because we are looking at the weighted average. This is important because if we have the entropy of x, this entropy is always bigger or equal than the entropy of x given y. If x and y are independent, then this is exactly equal. However, if we look at one specific value, it is possible that actually we grow more uncertain given a specific outcome. So because x is dependent on y, knowing what y will be gives us more uncertainty. And we will see that it is the case when we are calculating the conditional entropy in this example. So let's calculate that. We're going to calculate the conditional entropy of x given y, where we know that Peter can start. So y is Peter. We know Peter can start. If we calculate this value, all we have to do is minus, looking at those values, 0.25 times the 2 log of 0.25 plus 0.25 times the 2 log of 0.25. Now you're probably wondering, well, in my formula I said we have to multiply with the probability of y itself because we are looking at the weighted average. However, right now we are only looking at one specific outcome for our y outcome space. So that means we do not have to multiply with the probability of y because it's already known what the probability of y is. If we look at every outcome in the y outcome space, then we do have to multiply with the probability of y. And if we calculate this entropy, we see that this value is equal to 1. But the entropy of x that we calculated before was 0.9709. So we see that knowing that Peter can start the match, we actually grow more uncertain of the outcome. And actually, if we think about it logically, that's true. If Bob can start, we have a probability of 0.35 and 0.15 of winning. So we are more sure that Bob will win because he has a higher probability. However, if Peter can start, we see that they are both equally likely to win. So if we know that Peter starts, if it is given that Peter starts, we actually grow more uncertain of the outcome, which is logical in this case. Now, we can also calculate, of course, the complete conditional entropy of just x given y, which in our case will result in minus 0.35 times 2 log of 0.35. And now we do have to multiply with the probability of the y, which is 0.5. Probability of y is given here to the right of 0.5 plus 0.15 times 2 log of 0.15 multiplied with 0.5 plus 0.25 times 2 log 0.25 times 0.5, and the last one, which was also 0.25 times 0.5. And if we put this all in a calculator, we will get to the value of 0.9406. And this is indeed smaller than the entropy of X itself. And this shows that we are more certain of the outcome given Y. And Y can be that either Bob or Peter starts our match. And because Bob here has the advantage, that means that the entire entropy goes down a little bit. Now, the entropy has a nice touch to it because we can do some rewriting with formulas. The entropy of X given Y is the same as the joint entropy of X and Y minus the entropy of, minus the entropy of Y, which is good. With that, with entropy always comes the notion of information, how much information something gives. And we also have conditional information, of course. Conditional information is just the same, can be calculated with the entropy of X minus the conditional entropy X given Y. This just says how much information does our variable give. And coincidentally, this is actually the same as the entropy of Y minus Y given X. Or the information of Y given X is symmetrical. The information of X given Y is exactly the same as the information of Y given X. And with that, we can also have the relative entropy. A relative entropy, also called the Kullback-Leibler distance or divergence, was developed by Solomon Kullback in 1907 until 1994, and Richard Leibler in 1914, who lived from 1914 to 2003. They said we can actually check the differences in two probability distributions. They are saying if we have two distributions, namely P and Q, we can see how similar they are by looking at a different version of entropy, namely relative entropy. So we're looking at the probability of X given Xi, and let's say Xi is, let's not say Xi, let's say we're looking at a value inside our P distribution, so Pi is a member of P. This is multiplied with the 2 log of pi divided by qi. And this will always be positive. If it is exactly 0, it means p is q. If it is bigger than 0, it means that it's a measurement of similarity. And it's also very important to note that the similarity of q to p is not the same as the distance, the Kullback-Leibler distance from q to p. If you want to have a symmetry function that is defined as the symmetry of pq, which is just a half of p to q plus the Kullback-Leibler divergence from q to p, like that. And you may be wondering, well, what can we do with this formula, with this relative entropy? Well, let's go back to the last example of last video as well. We had the probability, let's call it p, of the people passing by. We had 3/10 for a car, 1/2 for a bicycle, 3/20 on foot, and 1/20 for something else. And let's say someone else measured something differently. Let's say p is actually our distribution, which is actually true, and q is distribution which someone else measured of 1/10, 2/10, 6/10, and 1/10. And someone else, a third person, also had a distribution with 4/10, 4/10, 1/10, 1/10. If we check what the distance is between p and q, we can just fill that in. We would get the, let's say, 3/10 times the 2 log of 3/10 divided by 1/10. We are comparing this one with the first one, and then we are comparing the second one with the second one. We're not doing every combination, we're going through it with each index. Plus a half times 2 log of 3/2 divided by 2/10, plus all the other the other ones, so 3/20 and 6/10 and 1/20 and 1/10. And this will result in a value of 0.7864 and more. If we were to calculate the distance from q to p, we would get a value of 0.8771 and some more, showing you that how similar q is to p is not the same as how similar p is to q, which may be counterintuitive, but that's how distributions work. And this Kullback-Leibler distance is used a lot in machine learning and variational autoencoders. And for the last, let's say we are going to compare p and r to show you that these two distributions are more similar, because if we calculate this one, this will give us a value of 0.0741. And this does not have a like kilometers, or there's no measurement. It's just saying that if I have two distributions or even more, I can see which distribution is most likely to be the correct one, or most similar to the distribution of p. And in this case, it is the distribution of r, because that value is the lowest. And that's how the Kullback-Leibler divergence works, also called relative entropy or discrimination entropy, and it's used to compare the similarity between probability distributions.